Hello. What we're doing today is going over the results for the Speeding Up, Slowing Down lab for Trial 1. And that's going to help you figure out how to answer some of the questions for Trials 2, 3, 4, and 5. So ideally, we would do this together in class, look at things in real time in class, and then go over this, and I would explain how we know these answers in class. So the goal is before you go over the Speeding Up, Moving in the Positive Direction, or Speeding Up, Slowing Down lab, Trial 1, you will have looked at the video for that and made some predictions for what the graphs would look like. So that's on the left side, I believe, letter E. And then what I'm going to do now is go through all those aspects of Trial 1, and then the goal is for you to have predictions for Trials 2, 3, 4, and 5. Ideally in class, you'll collect data for one of those trials. We'll present the results, we'll discuss it, compare it with your predictions, and so forth. If you're a VLA student, we'll handle that a little bit differently. But the goal is always to think about things and make some predictions before you see the results, and then compare the results with what you predicted so you can have a better understanding of kinematics graphs. All right, so in trial 1, what we've got here is we've got a cart starting here going down the hill. We think of the motion sensor always as 0 position, and motion sensors can only point in the positive direction. That's a little bit of a lie because you can change whether a sensor setting, but for our purposes right now, this is going to be 0, and away from it is going to be in the positive direction. So if you're moving, the cart is moving away from the sensor, it's moving in the positive direction. If it's moving toward the sensor, it's moving in the negative direction. So we're only interested in the graphs for the regions when the hand is not touching the cart. So after the cart's released and before you catch it at the end of the ramp. So in terms of thinking about this, a motion map showing both velocity and acceleration vectors. So this cart is going to start from rest and speed up as it goes down the hill. So the velocity would start at a 0, that's a dot, and then a short arrow and longer arrows. So those are the velocity vectors. Each interval of time, since this gains velocity in the positive direction, it's like we're adding extra velocity. Well, an acceleration by definition is a change in velocity. So the way you could think about how an acceleration vector for a motion map relates to the velocity part of the motion map is if we start with a 0, we add this positive acceleration arrow, we get this. We have this short velocity arrow, we add another acceleration arrow, we get a longer velocity arrow. Have this, add this, get this blue arrow, and so forth. So essentially, this is pointing in the same direction as the velocity arrows. We add this up. We'll see later if the velocity and the acceleration are pointing in different directions, that may very well be different. So because the velocity arrows are pointing to the right, we've got positive velocity. Because the acceleration vector is pointing to the right, we've got positive acceleration. So my graphs down here I made, actually that's not really needed, I suppose. I made predictions like this. I had a pretty good understanding of things. Note the graphs again only show the times the cart's left my hand, and we're showing general shapes. So the acceleration graphs especially can get quite bumpy because of how the sensor collects data. Essentially, it collects data only for position and time, and then does some mathematical calculations where it's taking derivatives to find the velocity and the acceleration. And that's a calculus term. So it's not really collecting acceleration data, it's kind of calculating it. And if it doesn't have very many, any small imperceptions or inconsistencies rather in position data, amplify as we go on and get velocity and acceleration graphs. All right, so let's take a look at this. By the way, the only difference we have here that I forgot about is my position graph has the same shape as what I predicted, but it's a little bit above 0. Because the cart, you can't start at the motion sensor. You need about 6 inches of distance for it to actually read correctly. Okay, so in this case, we've got a graph. It's curving up. That's an exponential increase. So if we used our slopometer that we've talked about in the past, the slope starts at 0, slope becomes positive, slope becomes more and more positive. So the slope is increasing. The slope is positive at all times after the start of the graph, and the slope of a position time graph represents velocity. So that should make sense, because if our slope is increasing, our position is increasing more and more quickly, and our velocity is also increasing. We can see that in the motion map up here. So for a velocity time graph, if we look at the slope of this graph, we think about change in the vertical axis over change in the horizontal axis. So that is how rapidly the velocity is changing. And when we had simple constant motion graphs, velocity graphs were always flat. Well, now they're not always flat. So in fact, here it looks like a diagonal line. So the slope is still constant, and the slope is positive. Well, the slope of a velocity time graph tells us acceleration. So if we have a constant positive slope on this graph, we have a constant positive acceleration down the ramp. Hopefully it makes sense that it's a constant positive acceleration because this ramp is a constant angle. So now, in order to think about the acceleration graph, we need to think about how velocity is changing. Well, velocity is increasing at a consistent rate. So my acceleration should be a constant positive value, since my acceleration or my velocity is increasing at a constant rate. So the slope of the acceleration graph is constant. The slope actually is 0, so that says we do not have a changing acceleration. And these graphs should agree with this. So I said I had a constant positive slope to my velocity graph, which means I have a constant acceleration. Notice my velocity is increasing consistently. My acceleration is always the same for all these intervals. So hopefully that makes sense. You might also want to think about, well, what if you had this ramp angled at a steeper angle or a less steep angle? How would these things change? I think it would be tough to tell the difference here, qualitatively or quantitatively. Here, I think these graphs would appear steeper for velocity, and I think the acceleration graph would be still a horizontal line, but farther above 0 acceleration. Hopefully those help out, and hopefully they help you make predictions to the rest of the lab.